Okay, we are going to continue the discussion for circuit families, and let's go over quickly uh, over the methods that we have covered in previous lectures. So circuit families that we looked at, and certainly we mean here CMOS, uh, not to be confused with the DJT circuits. Um, in digital electronics, we have discussed those earlier in the course. Um, but the circuit families that we have covered, we looked at complex CMOS, where we have a PMOS network and an NMOS network. The NMOS connected to ground, the PMOS connected to uh, power supply. The output is pulled from in between here, and the inputs feeding both networks. We looked at these type of circuits. We looked at pass transistors, where we have, this type of circuit control here and A. This is the function. We looked at transmission gates, uh, similar to pass gate, except we have um, extra transistor PMOS here. So this is control S, this is S prime, this is A, and this is the function. We looked at tri-state as well, where we have the output is controlled with a control signal here. Okay, and here is the input A and input A here as well. This is inverting tri-state input. Some people like to refer to pass gates as non-inverting tri-states. I don't like that terminology, but anyways, it's there as well. Then today we will cover other type of circuit families that they try to minimize the load and the size of the PMOS network. Let's say, for example, you have a NOR gate here, and these methods that we are trying to look at, they're basically what they are trying to do here is that they, um, oops, cancel that. They try to remove this PMOS network, and there is the pseudo-NMOS method where it replaces all of that with just a simple PMOS connected to either ground or control. And then there is that method of domino circuits, domino or and dynamic, where the instead of connecting the input to ground or an enable, it will be connected to clock. So today our purpose is remove the PMOS network here and discuss the circuit families that does that. Obviously, they have advantages and disadvantages. So, for instance, for every circuit family here, complex CMOS, they suffer from slow rise because of the PMOS network. The pass transistor suffer from the weak one logic here because they charge F here in the case of 1 to VDD minus VTN. The transmission gate here, they are really excellent for mux and flip-flop implementations, but they suffer weak drivability at this F here, and so you have to add inverters, and that seems to be an overhead. The inverting tri-state here, they are excellent at implementing interfaces to shared buses, but they again suffer from weak drivability through these PMOS. So every circuit got its advantage and disadvantage, and really what dictates the most appropriate circuit is the specifics of the design and constraints of the circuit. Okay, so so this is our focus in this lecture. So what we have here, whoops, got moved backward. What we have here, we're going to cover three topics: the pseudo NMOS logic and dynamic logic, and we revisit the past logic. In terms of, as we said, what we're trying to do here is that we don't like in complex PMOS these uh, stacks of PMOS. PMOS tend to be weak. They have um, weaker mobility compared to NMOS. They tend to be slow, in particular when they stacked, and they have large load on the driving gate. Okay, so it's good that we can get rid of them. So we're uh, trying to get rid of them at this lecture. One idea is remove the entire PMOS stack and replace it with just a simple PMOS transistor. And this type of circuit is referred to as pseudo-NMOS. Okay, so seems to remove the entire PMOS circuit, and notice that the input is just feeding into this NMOS here. Okay, so that's my input here, which is Vn. Vn is not fed to the PMOS stack because the PMOS stack is just a single transistor with its gate connected to the ground. So it is on all the time, always on. I like to call it always on. Okay, so very interesting design. But what happened when this PMOS is always on and this NMOS is on? So for instance, you have a logic of 1 here. Okay, the input is 1. So what's going to happen that the NMOS and the PMOS will fight, and that there will be a short circuit running through the PMOS all the way to the NMOS. And to simplify what happens, really, we can think of the PMOS device as a resistor and the NMOS as another resistor, and voltage divider rule will tell me the value of the V out. Now, clearly, what I want in this case is that the V out should be low as much as possible. So at the receiving end, whatever gate here receives the input, it will interpret this V out value as 0. If the PMOS was strong enough to pull this V out so that it will not be interpreted as 0 logic in the receiving gate, then you have a faulty design. That seems this design depends on ratio of the PMOS to the NMOS. So the ratio of this PMOS device to the ratio of this NMOS device makes this design as ratio design. We don't like that. That's a major disadvantage of this design, along with the fact that you have a short current when the input is 1. So in general, these type of circuits, you have to be careful when you use them. And typically the guideline is that the PMOS have to be fourth effective strength of the pull down network. So that way, if you look at the characteristic curve here, where we are plotting V out versus Vn, you would see that a stronger PMOS pushes out the transfer curve to the right direction and higher. So much so that you could end up with the V output at we call it V output low, V output low, that will not be interpreted as 0 with the receiving logic. So you really would want to have as steeper curve as possible. And at the same time, you would want the PMOS to be strong so that it will pull up the output high in reasonable amount of time. And that's why this ratio issue makes this design not appropriate for because of these issues, and designers have to be very careful when they use this type of design. Another improvement to the previous design, instead of having a ground here, you can remove the ground and use an enable signal here. And basically, this enable signal, it will have a value of a 0 to turn this PMOS on whenever you don't have a 0 on the or whenever you don't have a 1, I'm sorry, on the input, so that you avoid this short current. The only disadvantage really of such implementation is that um, designing this signal is a challenge. It's not trivial, and therefore you have to be very careful in designing, and you might end up losing area and power in designing and producing the signal compared to the power that you're trying to save. Okay, here's an example of, he says that whenever we have a short circuit, and basically because you will have uh, the current running through the PMOS and the NMOS, whenever this NMOS is on, and you will burn basically uh, around a current of 36 milliamp when you are using VDD of 1 volt. Of course, this is an expanded example in your textbook. You can look at the more of the details of the textbook, but really what we care about is that for every one of those situations, you're going to end up burning 36 microwatt. That's a lot. That's a lot for this type of stack. So for instance, if you have a memory which has 32 words and 48 bits and implemented in a RAM, and RAM loves using this design and RAM designers love using this design, and the reason is that such a design is appropriate for wide NOR gate, and it supports that beautifully. Okay, and you have this PMOS up here, and so the ROM, it has different implementation. Um, there is the NAND implementation and the NOR implementation. The NOR implementation loves such a design where you have a PMOS at the top. Now, in this circuit or in this exercise, he's trying to estimate that if you have 32 words, okay, where you are activating one word, and in that activated one word, you will not have a short circuit, but in the rest 31, you will have a short circuit. And if you have 48-bit ROMs of data, in every line of bit of data, you will end up a chance of 50% burning a short circuit power. And in this case, you'll have 24, 50% by 48. So this simple ROM design and small design will burn 1.98, about 2 milliwatt in this small design. That's significantly high, and we have to be careful when we are using such ROM design. Okay, so we said that the PseudoNMOS has a problem, which is that it is ratioed logic, and at the same time it burns quite a bit of power. Now, what happened is that we would want to, oops, we would want to explore removing this enable, okay, and replace it with a clock. And this clock phi here is that sort of synchronizes the evaluation of my circuit. So simply this clock goes into two phases, like any other clock, where the clock is equal to 0 and the clock equals to 1. During the clock equal to 0, we notice that this will enable this PMOS, and it will charge up this output right here. Okay, so we will do a pre-charge. We will have during that pre-charge, this stack is disabled, and then the clock becomes 1, and when the clock becomes 1, this becomes off the PMOS, and then we will discharge the output conditionally based on the value of the input. Therefore, you will see that the circuit has two phases, pre-charge phase and evaluate phase, based on the value of this clock. So in this case, what we are trying to do, we're trying to avoid the short circuit between the power supply and the ground. And by having a pre-charge phase when the clock equals 0 and the evaluate phase when the clock equals 1. There are two flavors of these dynamic circuits, and of course we would refer to them as dynamic circuits because they are based on this clock. The one implementation, it implements the function. So right now what we are doing, we are kind of explaining the skeleton of the design. So basically it consists of a pre-charge transistor, PMOS, connected to the clock, and an evaluate NMOS transistor connected also to the clock. And then you have the function evaluated here in the middle, and notice that the output is pulled out just from the bottom of the pre-charge at the top of the function. You can, if you guarantee that this function stack will be off during pre-charge, we can remove this evaluate transistor. And this kind of why we can remove it. Well, let's just explain why we have it in the first place. This evaluate transistor right here, its main job is to turn off the uh, 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 the, the current path to ground during phi equals 0 during the pre-charge. But if we guarantee this, that this will happen with the inputs, meaning those inputs will be zeros, for example, during the pre-charge, then there is no need for this NMOS transistor right here. So two flavors, and both are correct, although this is preferred if you can guarantee the condition on the inputs. They refer to this as footed, and this is unfooted. Okay, let's go back. Oops. Okay, let's go further here. Now, the monotonicity of the circuit means that the inputs on the circuit, and for in this case, we are taking just one input. You can have more than one input, obviously. And you can see that here we are implementing an inverter where the output here will equal A prime. But we have to be careful of the transition of the input on A. And basically, if we consider that A equals 0 and remains equal. Now notice that this arrow here, it means when the clock changes from pre-charge to evaluate. So, and I'm sorry, let me restate this again. This arrow means that this is the transition during the evaluate. So this is the transition during evaluate. So this is the transition during evaluate. And we know that the evaluate, it is when the clock equals 1. So can I transition the inputs during the evaluate? Well, during the evaluate, when the clock equals 1, so this is off, and this is whoops, and this is on. If A is 0 and remains 0, there is really no harm. And similarly, if A is 1 and 0 is 1, it will be discharged and no harm. Similarly, if A was 0 and then becomes a 1, we will discharge the output, no problem. It is when A is 1 and then it changes to 0. And this is because that if A is 1 and then it changes to 0, watch this, 1 and 0. What happened that the output will be, which is right here. I call it F. It should be Y actually. Oops, sorry. It should be here Y. Okay. It is. You will notice that the output here was pre-charge, during the pre-charge, and then we come to the evaluate here. Notice that during the evaluate, the Y goes to 0. Why? Because the input is 0. Then the input makes this transition, dangerous transition. Well, suppose I should go back up, but it cannot, because the only way we can pre-charge this node is during pre-charge when phi equals 0, when the clock equals 0, but the clock still is in 1. So now will remain here giving output of 0, and this is erroneous output because the input is 0 and the output should be 1, but the output cannot be charged to 1 until we get into the clock here, sorry. Okay, so during this time the output remains 0 erroneously, and therefore we should disallow this type of transition of input should not transition from 1 to 0 during the evaluate. This is illegal. So in this case, another issue is um, that when we have a, a, an input here, and in this case A with the output X, and then this X is connected immediately to another input of a dynamic. So this is dynamic circuit, another dynamic circuit, and you will see that if X if A, sorry, is 1, then during the evaluate, which is right here, okay, X will be discharged right at the through the NMOS and the evaluate transistor, and therefore what happened is that during this discharge, okay, you will see at this small time here X is 1, and what it does, it was erroneously discharging Y. So Y here could fall off all the way to ground or halfway to VDD, okay? And this kind of connection should be disallowed again, because what we want here really is X equals A prime and Y equals A. But in this case, you will notice at the beginning of the evaluate, X will be 1 for a very short time, and during this short time, this could erroneously discharge Y. We have to stop that. This is illegal connection. So, oops, we'll go back here. So, what we need to do to improve on this dynamic circuit is we have to separate these dynamic circuits with a static inverter. So right now you have this is one stage of dynamic circuit followed by another stage. And the dynamic circuit in this state has an inverter following the dynamic circuit, and another inverter following the dynamic circuit. We call such a static inverter and dynamic circuit, we call this type of circuit domino circuits. And in this case, what we do, if we are doing a transition, we are enforcing the transition that goes from 0 to 1, which is legal. We are trying to implement to prevent the illegal transitioning of 1 to 0, as it was in the previous case. So here, the transitioning that happened to X was, it was 1, and then it became a 0. This is illegal transitioning. And what we are trying to do here in the next design by adding this static, that if there is a transitioning to this input, it will be from 0 to 1, which is legal transitioning for the receiving dynamic gate. Okay, and you can see that in the illustrated in this diagram. So this is the concept of domino gates, as they force certain transitioning of the signal. Either they are static, they don't change, but if they change, the inputs to the dynamic circuit, they change from 0 to 1, which is the legal case. You can read for the design of a multiplexer using domino, but I'm gonna be selective here in what I explained. So that was a reading material. In terms of domino circuits, people like to produce always the output of a function and its inverter, and there is a reason for that, because since we are forcing inverter at the output of the dynamic gate, the domino circuits tend to be true logic circuits, and there's a problem with that. What happens if you need to feed a negative logic or an inverted output to a dynamic circuit? Then we are stuck here. So we have to provide always the function and its complement, so that we can supply all kind of inputs to the functions. And this is excuse me, and this is the dual rail domino. It is a function, or it's a circuit, which produces the true output of the function and it's inverted. So this is y and this is y prime. Let's take an example here. So in this case, what we have is that we want to generate the a and b function. So here is y, which is equal a and b. Now, obviously, this is the static inverter. I have to have it because I'm implementing domino circuits. And obviously, before the input to this will be y prime, which is a NAND b. Okay, and then I wonder why is that happened, but anyway. And then we have at the other end, I'm implementing y prime, which is a NAND b. And here it will be y, which is a and b. It is easy to produce, let me just scratch this out here. It should be y prime, which is equal to a b NAND. Okay. So at this point, it's easy to produce the NAND by just simply having this PMOS inverter for the pre-charge and the evaluate, and a stack of two NMOS transistors, one connected to A and one connected to B. There you have it. You have here A, B, NAND. Okay, well, how then I can produce A, B here with just a negative logic here? No, remember that this is here will be the output of this stack here. And to do this, this is where De Morgan comes handy, where I can say that A dot B, okay, equals A dot B inversion, and this is equal to A prime or B prime inversion. So this inversion comes for free because we are designing a stack of NMOS transistors. So that's good. But then I have to have this A prime or B prime, and this is what I'm doing here: A prime or B prime. So at this point, what I'm gonna get here is that exactly I'm gonna get a prime, or b prime inverted, and that produces for me a and b, and after the inverter it will be a and b, which is the y prime. So this produces for me dual function where I have the y and the y prime. You can take this further to implement other function like XNOR and XNOR, and I'll leave this as a reading material for you to validate this and study it. And we will now look at some of the issues and problems for dynamic circuits, and one of them, for instance, is the leakage problem. And the leakage problem basically is the following: if we are at um, the evaluate phase, which is when clock equals 1, and in this case, A as well equals 0. So supposedly that here we have a VDD value. Unfortunately, as we've studied earlier, that there is, even the transistors are off, there is leakage current. And this leakage current, what it does is will leak this value, and especially if this period is a very long time, it will leak all the way to 0, and that will cause erroneous result. And remember, this is this has to have one of the two conditions: leakage is high, and this period is high. And if that happens, then we might run into this situation. Now, one fix to that is that we can compensate this leakage by adding a pull-up here, a weak pull-up or a weak keeper, which is activated by the output of the static inverter in the domino circuit. Because if we have here VDD, then the output here will be 0, and this will be active, and it will try to compensate this leakage current. This weak keeper has to stay weak, because if we need to pull down this node all the way to 0 when we evaluate, when clock is 1 and A is 1, then there shouldn't be any fighting with this pre-charge. So it has to be weaker and easy to be overpowered. Okay, so this is the solution for the leakage problem. And another problem is the charge sharing problem. And basically, the charge sharing problem says that suppose in the um, uh, suppose in the start of the evaluate. So this is my clock here, and I am doing an evaluation, right? And at the start of the evaluate, A was 0, so A was 0, and B is 0. Then A changes its mind in the middle of the evaluate and turn to 1. That's not a problem. That's legal transitioning. So A transitions to 1, and in this case, B still 0. So we are supposed to keep this VDD as VDD. Unfortunately, because we have capacitance at this node and capacitance at this node, we will have to have, or we will have a phenomenon known as charge sharing. And basically, charge sharing comes from the conservation of charges, uh, which says that the charges in a system at the beginning of an event equals to the charges in the system, to the total charges in the system at the end of certain event. That is for a closed system, meaning there are no charges that come from the outside, and there are no charges that escapes our system. And in this case, what we have is that the charges at this point in this system equal to the this is whoops, didn't intend to do that, equals Q at the beginning here equals to CY times VDD. Now I'm assuming that this is that the CX initially, the voltage in CX initially is 0. Okay, so that's the total charges in my nodes CY and CX. Now when X, I'm sorry, when A changes from 0 to 1, then we will have some of those charges come over here and charge this voltages here. Okay, now so the same number of charges will equal to Cx plus Cy. Okay, and let's refer to the final voltage as, for instance, Vx, because when we distribute the charges between these 2 points, we will have a final voltage of Vx. So what's the final voltage at this node after the distribution of charges when A changes from 0 to 1? It is equal Vx equal Cy over Cx plus Cy times VDD. Obviously, we solve for Vx from these two equations. Now, this is could be okay, and this could be a problematic if, say, for example, Cx and Cy are of equal values. And in this case, this dangerously can pull down the output node here into a level that the next gate will interpret this as a 0. And it's not a 0. It's basically we're dropping in the voltages here because of the charge sharing. So we need to prevent this, and one way to prevent it basically is, let's see if we go further, is to pre-charge this internal node. And this pre-charging, remember we said that the initial voltage, the initial number of charges are Cy times Cy times VDD, and now because of this we will add also Cx, so it will be initialized to VDD, and this when this turns on later, we will not have any drop of voltage at the Dy. Okay, now domino circuits are known to be fast, and they were used in the past, particularly in the 90s, for fast circuitry. Unfortunately, they are very sensitive to circuits, and you can see that if you are in a stack of this function which implement the f function of the domino circuit. So this is phi here, and this is phi here. This is the input. Any noise here in this input can start erroneously discharging this output, and therefore they tend to be very sensitive. Now we'll study later on what type of noises we have in the system, but typically they are during to crosstalk, charge sharing, power supply noise, and so on and so forth. And um, all of this because of this intensive activity that happens in your circuit. So any pulse here that comes through the inputs can really cause a problem for your circuit. So these circuits are tend to be really noise sensitive, and that's along with the fact that they burn lots of power, have diminished their popularity as a choice for circuit design. Okay, as we indicated that they have high power as well. Okay, um, okay, so pretty much we indicated their advantage and disadvantage. They are fast. However, domino. In summary, the advantage: they are fast. Disadvantage: they are susceptible to noise, and they burn lots of power, lots. Okay. Now here we review some of the test transistor and transmission gate that we have indicated in the earlier of the chapter. And we say that one of the problem of the pass transistor is that we tend to charge this node, or this node suffers that it is charged to VDD minus VT. A fix for that will be is to have this weak pull-up, and this is an inverter which activates this pull-up. So if we have here a VDD, this will be 0, this will turn this on, and then we will charge this node all the way up to VDD. So that's this type of logic called lean integration with pass transistors, and briefly LEAP. And also the complementary pass transistor logic, where you really you don't basically use the inverter here. Rather, you use an internal node to activate this pull-up, but this requires that you use um, or you produce the function and its complement. So this is here will be y, and this will be y prime, and this is the activation of of these PMOS transistor, because now you activate them with an internal node rather than an external node, which tend to be an advantage for CPL. In summary, or in conclusion, there are many circuits that so we covered a few, but there are many other circuits that you can look at. These are left for obviously postgrad class. We will um, uh, stop at this point and uh, not discuss other circuits. Obviously, you are more than welcome to go over the other circuit types for extra reading, but we're going to stop at this point. Thank you.